Hi, welcome to Complex Analysis. This is the second session on the series on Laurent series. So let us get started. Today, if time permits, I think I should be able to do two things: Leibnitz Rule and Laurent Decomposition. So what does Laurent series say? Let's just see whether I share the screen. Yes. Okay. Yeah. It says that suppose I have a function of two variables f of x, y. Okay, and I define a new function g of y, so that integral f of f x y dx, let us say some interval a to b. Then under suitable conditions you want to say g is differentiable, and therefore you want to compute the derivative of g. What does it say is it's exactly same as partial derivative of f with respect to y and differentiating this, right? So let us write it symbolically. That means d by dy of integral a to b f of xy dx. Okay, so I am differentiating. Now I have to push the differentiation under the integral sign. This is a to b df. Since it's a function of two variables, you write it like this: del y of xy dx. Okay, this is what the so-called Leibnitz rule of differentiation under the integral sign says. So we have to naturally make certain assumptions about the function f. First, this has to make sense. So we will assume f is differentiable. So since I want to say it's a differentiable, then so let us the domain be a rectangle of the form AB cross CD. If you want, you can assume it's some open into open, but I am going to deal with only this. Okay, this is, so I want it to be continuous on this, and this integral should make sense. Therefore the easiest thing will be, I want del f by del y continuous again on the rectangle. Okay, continuous on the rectangle. Okay, right. Now notice that the rectangle we have chosen is closed and bounded, therefore it will be compact, therefore this will be uniformly continuous. Okay, right. So these are the assumptions we want to do. So let us make it as a theorem now. The theorem says let R be the rectangle AB cross CD, and let f from R to C be continuous. Okay, so I am talking about complex valued function. So define g of y to be a to b f of xy dx. Okay, it's very easy to check under the stated condition g is continuous, but we are going to prove directly and further assume that del f by del y exists on R and is continuous on R. Then g is differentiable. This is a function of y, right? And therefore g dash y, which is, as I said, d by dy of g at y. This is nothing other than a to b integrate this del f by del y xy dx. As I said, this is continuous on the entire interval, therefore it's continuous on this interval a to b, therefore integration exists. Okay, this integral makes sense. Okay, right. So we want to prove that. Usually you might have seen a proof of this. In all probability many of you may not even remember. Okay, when f is R valued, real valued, but we want it to be complex valued because we want to apply in complex analysis, so there is a slight care required. Okay, we will look at it as we go along. So when I want to say this g is differentiable, what is that I have to do? Okay, for h is near to 0, then I am going to look at g of y plus h minus g of y by h. I want to say this goes to this integral a to b del f by del y of xy dx. This is what I want to prove, right? So what does that mean? That means you are going to give me an epsilon positive. I have to show there is a delta positive, so that whenever mod h is less than delta, this distance g of y plus h minus g of y by h minus this integral a to b del f by del y xy dx, this is less than epsilon. This is what we want to show, right? So let us go prove that. So let us look at. So what is g of y plus h minus g of y? This is going to be a to b f of x y plus h, okay, dx minus a to b f of xy dx. Using the linearity, this is going to be a to b f of x y plus h minus f of xy, the whole thing into dx. Therefore y h is going to be 1 by h upon this value, and this 1 by h, since it's independent, then I can prove it, I can push it here, right? Now the moment I see f of x y plus h minus f of xy, I want to estimate this, okay? Therefore what do I want to estimate? Therefore I want to estimate g of y plus h minus g of y by h minus integral a to b del f by del x del y of xy dx. This is going to be again using linearity of the integral f of x y plus h minus f of xy by h minus del f by del y xy and the whole thing times h. But I want this to be modulus, therefore it's less than or equal to modulus here. Yeah, d. Have I done correctly? I hope I have not done any mistake. Yeah, right. Okay. Now the moment I see this one numerator f of x comma y plus h minus f of xy, a natural tendency is, if you have learned real analysis from me, you know that I would like to use mean value theorem, right? So I would like to use mean value theorem to this. But remember, f is complex valued. Okay, so okay, for a fixed x, this is going to be a function from c to c. Okay, this is a function of y, that is fixed x, then this is y going to f of xy. And for complex valued function, mean value theorem is not true, does not hold. You had already seen this. If you had watched my complex analysis videos, there was one video only talking about functions from R to C. Okay, so there I have done various things: differentiation, integral, integration, and fundamental theorem of calculus, etc. Right? So we know that's not true. Therefore, I cannot apply mean value theorem blindly. So for the time being, let us assume f is real valued. So you understand why I am putting a restriction now? If that be the case, then I know there exists a y dash. So now again let's look at the picture. This may be my x y, this may be my x y plus h. So there exists a point here x y dash, where y dash lies between y and y plus h. Because it looks as though h is positive, h could be negative also, that's why I would write between y and y plus h. If y plus h is near below, then it will be somewhere here, right? Therefore it is going to be f of x y dash into h, okay, for some y dash which lies between y and y plus h. This is by mean value theorem. for real valued functions from real analysis. Right, now look at that, I am in good shape though. There is a h here, that h cancel with this, therefore I am getting f of x y dash. That's it. Okay, I'm sorry, I am being a fool. You see that? Meanwhile, the theorem should say, okay, del f by del y, the derivative of f with respect to y, and then I am sorry for this stupid mistake anyway. Right? Therefore, whatever I wanted to estimate is less than or equal to a to b modulus del f by del y x y dash minus del f by del y x y into dx. Right? If you learn fundamental theorem of calculus, etc., from real analysis, these are the very standard way of doing these things. It's very easy. Now, what do I know? I know this function is continuous. Therefore, this is uniformly continuous. Del f by del y is uniformly continuous on the interval on the rectangular. Therefore, that means whenever some x dash, okay, given epsilon positive, there exists a delta positive, so that this I can make it small. Whenever the distance between, that is distance between x dash y dash and xy is less than delta, then the distance between del f by del y x dash y dash minus del f by del y xy will be less than epsilon by b minus a. You should know why I want b minus a. I want to say this less than epsilon, then the length of the interval will be b minus a. I want to cancel. That's the reason. Okay, right. Now notice that why I need uniform continuity. See, as I am integrating over x, therefore this x will also vary. You understand that? Therefore, if I have different x and different y in the same thing, this may be a rectangle, my x may be here, xy may be here, okay, and this may be my x, y plus h, this may be my x dash, y dash, sorry, x, y dash. You understand that? Yeah. So, what I want is, therefore, there exists. Okay, now let's look at what is the distance between x and y plus h and x and y. Okay, this is nothing other than mod h, right? Therefore, if mod h is less than delta, then this fellow is less than delta. If this fellow is less than delta, this one, this fellow, that is del f by del y of x y dash minus del f by del y x y, that's less than epsilon by b minus a. Okay, this must be true for all x y where in the rectangular. We are using uniform thing, right? For all x y in the rectangular, x y and x dash y dash, we said this. Okay. Are you following? So, what I have shown, therefore I have shown that, okay, given epsilon positive, there exists delta positive, so that whenever mod h is 0 less than mod h is less than delta, okay, then g of y plus h minus g of y by h minus integral a to b del f by del y of xy dx, this in modulus is less than or equal to a to b epsilon into dx, which is epsilon by b minus a, therefore which is equal to epsilon. Okay, so that means we have already proved. Okay, therefore we have proved if f is real valued, okay, and then we have proved g dash of y is integral a to b del f by del y xy dx. Okay, pause, review, proceed. Okay. Now the question is, what happens if f is complex value? Write it as f1 plus I f2. F1 is a real part, f2 is, instead of u plus iv, I am writing f1 plus f2. Yeah, right. This is the real part of f plus I times imaginary part of f. Okay. Then remember, if f is continuous, then we know that del f by del y is nothing other than del f bound by del y plus I times del f2 by del y, etc. Because remember, it's an aside. Recall, f equal to f1 plus I f2, then f dash t we have proved is f1 dash t plus I times f2 dash of t, etc., etc. Okay. That is why, unlike many books, I spend at least 1 or 2 sessions on functions from R to C, differentiation and integrations. Okay, we don't jump into functions from C to C directly. Is that all right? Okay. Therefore, now again, what is integral of f? Integral of f of x y dx is nothing other than integral of a to b f of f1 of x y dx plus I times integral a to b f2 of x y dx, etc. Right? Okay. And so this is going to be my g of y, therefore this is going to be my g1 of y plus I times g2 of y, and therefore g dash of y according to our definition is g1 dash of y plus I times g2 dash of y if these are all differentiable, right? But we know that by the Leibnitz rule can be applied to f1 and f2, therefore we get the result. Okay, please think over, understand, it's a very routine thing. Now you should follow that. Okay, now we want to use this to do something very interesting. Suppose I hope I will get it, a circle, highlight a select region, and okay, so I am not selected or not selected. Yeah. So suppose I have a circle, right, and another circle. This is the same center. Okay, this must be of the same region. Okay, they do not look like, they are supposed to be concentric circles. Okay, right. Okay, so let us say this is R1, this is R2. I chose a wrong one. Okay, I should have chosen this anyway. So this is R2, sorry, small r1. Okay, small r2 then. Okay, so this is annular region. So annular region is defined like this: region or annulus we define. Okay, let r1 be less than r2. Okay, this may be equal to, this may be less than or equal to infinity. Then we define, okay, a of r1 r2 with the center. This is the center set of all z and c, so that let's look at mod z minus a. Okay, this should be less than r2 and should be greater than r1. That's it. So this is your center a. Okay, so these are the points which I am looking at now. The points are going to be, this is my annular region. This is my a r1 r2. Okay, so we are going to look at functions holomorphic in annular region. So let me just simply write a for this, so that I don't have to keep writing, because there are too many things I would write, so it will be easier. Okay, what we want to do is I want to write f as a sum of two things, f2 plus f1. You see that I am not writing f1 plus f2. So f2 is holomorphic in the disk BAR2 and f1 holomorphic outside the disk. You understand this? So outside the disk, this is going to be f2 is holomorphic, sorry, f1 is holomorphic, f2 is going to be holomorphic inside the disk. And so what is the common domain there for them? The common domain for f1 and f2 is the annular region. Okay, so there when I add these two functions I get f. Please understand, yeah, the common domain for f1 and f2 is annular region. So I can add for every z in the annular region, I can add what is f2z plus f1z, and then what should I get? I should get f. And this f1 will also have an interesting property, namely, remember f1 is holomorphic outside a closed disk. Okay, if you want, make it closed disk also. Okay, here, right, this one what we want is that f1, therefore z goes to 0 as mod z goes to infinity. So that this, please understand this what we have done. So we have defined what is meant by an annular region, and I am starting with a holomorphic function in the annular region. What am I going to show? The annular region is the region which is, okay, enclosed between two circles. Okay, then I am going to write f as sum of two holomorphic functions f2 and f1, where f2 is holomorphic on the region enclosed by the bigger circle, and f1 is holomorphic outside the disk enclosed by the smaller circle, right? And not only that, since f1 is defined on except as a bounded set, so z goes to infinity, I want f1 z goes to 0. This is what we want to prove. This is what we call as a Laurent decomposition. So f equal to f2 plus f1 as specified is called the, I will write the Laurent decomposition. Why I want to say the law is that is unique. If I write f equal to some g2 plus g1 with the same property, then f2 must be equal to g2 and f1 must be equal to g1. Okay, remember, otherwise if I don't put that condition, I can always put a constant this. Suppose I got f2 f1 as above, then you look at this as limit z goes to infinity, f1 minus c will go to minus c, it will not go to 0. So I can always get such a decomposition. But what I want is to get uniqueness. Okay, we wanted the condition f1 of z goes to 0 as z goes to infinity. These are the things which may not be explained in the usual course, but as I said, if you are trying to follow my videos, okay, you want to master the subject in depth, you want to understand it in depth rather than passing exam. Okay, so please understand that. So this is the Laurent. In fact, the word Laurent decomposition may not even be common. Even in my book I didn't call it, if I remember right. Anyway, is that clear? This is our goal. This is our goal. Goal is to get such a decomposition. How do we get it? Okay, we are going to get f2 and f1 again as Cauchy type integral. Again, you see that it pays if you have followed my lectures videos from the beginning, because this Cauchy type integral is never explained in books. Okay, but we have spent time on that, so you will immediately realize. Therefore f2 will be integral of path integral of some function, okay, over a closed path by something of the form minus w minus z, okay, some g of z, w by w minus z, etc, etc. Okay, this is what we want to do. Okay, right, is that clear? So pause, review, proceed. Please go through this, understand, come back. So let us prove the uniqueness part. Suppose my f is f2 plus f1, which is also equal to g2 plus g1. What are the things? g2 holomorphic on b of a r2 f2 g2 and f1 g1 outside closed ball b of a r1, and f1 g1 goes to 0 as z goes to infinity. These are the conditions, right? Alright, now let's look at f2 minus g2, bring it here, and g1 minus f1. Okay, this is what call this f1 h2, this h1. Now notice that f2 minus g2, f2 and g2 are holomorphic on BA_R2, therefore h2 will be holomorphic on this, and g1 f1 will be holomorphic outside, therefore they have the common domain, they agree on the annular region. h1 equal to h2 on the annular region. Is that clear to you? Yeah, therefore I can this, okay, remember this is a holomorphic function on B of a R2. This is holomorphic on outside B a R1. It's complement. Okay, but these two functions agree where on the annular region. Therefore I can patch them up to give a function h. So h of z equal to h2 of z on BAR2 and equal to h1 of z on BAR1 complement. Okay, now it's well defined and they agree, therefore h is holomorphic on the entire complex plane. Pause, review, proceed. Right, now what do I know about h? See, remember, for mod, if mod z is greater than very large, then mod z is not going to be on the closed ball BAR1, right? Therefore h of z is equal to h1 of z for mod z very large, but this goes to 0. Yeah, therefore what we get is h is an entire function vanishing at infinity, that is, as z goes to infinity h of z goes to 0. Okay, therefore h is bounded on all of C by Leibnitz theorem. But at infinity it is 0, therefore h must be, so can h of z be constant for all C? Then C must be 0, because as z goes to infinity C should go to 0, right? Therefore C is 0, therefore h is identically 0 on C. But what does that mean? That means this must be 0. So f2 minus g2 must be 0 on the big disk. That means f2 is equal to g2 on the big disk, and similarly g1 must be f1 on the complement of the closed small disk, right? Therefore we have proved f2 equal to g2 and f1 equal to g1. So uniqueness is done. Pause, review, proceed. Now how do I get it? So these are all theory. Now I want to prove existence. We still to prove existence of Laurent decomposition. Right? How do I get it? That is where another thing comes. So let us assume I have something like R1 less than R less than S less than R2. My function f is holomorphic on the annular region A. Right? Now let us look at the path gamma r of t to be a plus r e power I t for 0 less than equal to t less than equal to 2 pi. Therefore similarly gamma is also defined. Okay, so these are the two things. Okay, this is another one. Okay, let's not worry about it's very difficult for me to draw pictures, so let us assume that. Okay, right. So I can define a new function g of r for r lying in the interval r1 to r2, g of r to be interval of gamma r of f, that is fw dw. Right, this is the path interval of f as r varies between anything. So I have a function g is a function from where to where, r1 r2 to c. Right, I want to show this is a constant. We claim g is a constant. So what does that mean? So if I have two concentric circles gamma r and gamma s, that means this is the same as these two integrals are same. Path integral of f over the circle gamma r is same as the path integral of f over gamma s. Do you understand this? Now how do I prove a function defined on an interval is a constant? Natural thing is to use differentiation. Prove that the derivative is 0. Right? So I have to prove the derivative is 0. So claim g dash of r is 0. That is g dash is 0 on, since this is an interval, then therefore that will imply g is a constant. Right? Okay. But I know how to deal with that. Therefore what is g of r? G of r, let us write it explicitly. It is b of a plus r e power I t. Remember, integral of f over gamma is integral a to b f of gamma t into gamma prime t dt. Okay, therefore gamma t is a plus r e power I t and 0 to 2 pi, and gamma prime t is r I e power I t dt. Do you understand this? This is g of r. So now this is, now I have a function of two variables. What are the two variables? Let's look at r and t. That goes to f of a plus r e power I t r I e power I t. This is a function of two variables r and t, complex valued function. And where is it defined? It is defined on r1 r2 cross 0 to pi. Okay. Now if you want to say this is only this r I can again take it. This is my r1, this is my r2. I can split my something like rho 1, rho 2, keep only r here. Okay. So on this I will apply the result, and this is true for every rho 1 and rho 2. Therefore the result will be true. Or are you following what I am saying? I can restrict this function to rho 1 close interval rho 1 rho 2, where rho 1 rho 2 are like this, and rho 1 rho 2 are arbitrary. That will follow the result. Okay, so the function is going to be constant on this, g is going to be constant on this. Since rho 1 rho 2 are arbitrary, that's going to be constant on all of the open interval r1 r2. Okay, because you should remember in the hypothesis I needed my rectangle to be compact. Okay, product of two compact closed and bounded intervals. Okay, these are the small things, but as you go along you should feel confident, you know that. Okay, that's why the textbooks may not explain these things and the teacher may not explain. They expect you to be mature so that you can do that. But let us understand this. Okay, right. So I want to show, so I want to look at, what do I want to look at? Therefore I want to look at, so I do not know a name for this, so let us call it say phi of rt. Instead of f I am having two functions phi of rt. Therefore my g of r is going to be 0 to 2 pi of phi of rt dt. Am I correct? I hope I got everything. Therefore according to Leibnitz rule for differentiation under the integral sign, this is going to be del f by del g dash r, okay, phi of rt dt. 0 to 2. Okay, therefore I have to find out what is the derivative of phi of RT. So what is phi of RT? RT going to, I may make mistakes because I'm just going through it in my mind and then writing this, and then gamma t will be R e power it, and there is also an I into e power, and that's it. Yeah, I wrote it correctly. Alright, yeah, right. Okay, therefore this, how to find the derivative? This is with respect to, so I want to find the derivative with respect to R. So let us compute the derivative of g dash of the derivative g dash of R. Okay, and this will be very interesting computation. Let's go ahead. So we have g of R equal to integral of f over gamma R, which by definition is integral 0 to 2 pi f of a plus R e power it into R I into e power it dt. Right. So according to our Leibnitz rule, d by dr of gr, which is g dash of r, is 0 to 2 pi del by del r of this function. Which function? This function into dt. Right. So we want to compute the derivative of this. Now let's look at, this is product of two functions, namely f of a r e power it into r I e power it. Remember, I e power it is independent of r, therefore del by del r of this I can write as f of a plus r e power it r I e power it. The whole thing is what I have to differentiate. If you want, put a square bracket so that you know where it is. So this is now what I e power it is this, therefore this is del by del r of this object f of a plus r e power it into r. So naturally I can use the product rule, right? So the product rule is going to give me, let me just make sure that I'm screen sharing. Yeah, so that is going to give me I e power it into del by del r of f of a plus r e power it into r plus I e power it is again common into f of a plus r e power it into del by del r, which is 1. Right? So now I want to find this derivative of this fellow. So let us try to do that. Here what is the map? It's a composite map. That is r going to a plus r e power it, and that goes by function. This is z going to f of z. So we have to apply chain rule. Okay, that is going to be, therefore let us call it, I do not know what name I have to give, let us say alpha of r or something. Then your function is f composite alpha of r, right? That is by definition f of alpha r, f dash of alpha r into alpha dash of r, right? So alpha of r is a r e power it, therefore alpha dash of r, that is d by dr. Okay, when I write a dash, it is with respect to the variable r here. So if, let us make it clear, that is going to be e power it, and this is f dash of z. Okay, this is del f by del z, so df by dz. Okay, of this. Right. Remember, we already proved a chain rule. If alpha is a function from a b to u, and from here it's a holomorphic function c, then f composite alpha dash at t. Okay, if you want to assume this is r variable, then it's going to be f dash at alpha of r into alpha dash of r, where f dash is the standard derivative, complex derivative, right? Therefore that's going to be f dash at a plus r e power I t into into e power I t. Okay, pause, review, proceed. So now we are ready for del by del r of f of a plus r e power I t into r I e power I t, that is equal to I e power I t into del by del of this we have just now found out, it is f dash of a plus r e power I t into e power I t, and there is also another r. Okay, f dash into r plus I e power I t into f of a plus r e power I t into 1. Is it okay? So this is what we found out. Now notice that this is nothing other than f dash of a r e power I t into e power 2 I t I r plus f of a plus r e power I t into I e power I t. Okay, we found out. Now the trick is, so we have found out g dash of r, that is d by dr of g of r is this fellow, 0 to 2 pi of, I don't want to write it, into dt. This entire thing into dt. The trick is, we want to use fundamental theorem of calculus, so I want to write it as 0 to 2 pi of d by dt of xi of t dt. Suppose I found such a xi, okay, but notice that if I want to use for Leibnitz rule, I have to make sure this d by dr, remember in the notation of Leibnitz rule, del by del y must be continuous on the rectangle, right? Now is this continuous on the rectangle? What is the rectangle? As I said, the rectangle will be, okay, r1 to r2 or whatever it is into 0 to 2 pi closed. And this, as I said, I can just restrict myself to something like rho 1, rho 2, 0 to 2 pi, etc. Okay, I don't want to repeat. Okay, so is it continuous? There is a subtle thing. What is the subtlety? See, you can see the map RT going to this object. Okay, this is continuous, except this is also continuous because f is holomorphic, right? RT going to a plus r e power I t is continuous, followed by composite of holomorphic function, a continuous function f, therefore this is continuous, product of two continuous function I into e power I t, therefore this part is continuous. Similarly, I can, when I want to show this part is continuous, but why is this continuous? I wanted the continuity of f dash. Remember, f is holomorphic, therefore f dash is also holomorphic. F is infinitely differentiable. In particular, f dash is continuous. So we could not have proved it earlier till, okay, are you following? So this is continuous. This is continuous function of r and t. Okay, right? Now let's come back. So the trick is, this integrand I want to write it as d by dt of some other c1 function, because then I can use fundamental theorem of calculus. Now let's look at this. See, you can see this again is going to be sum, therefore product of two functions, f is there, f dash is there, and there e power I t alone comes out. Okay, so therefore the derivative must have been this, though I have to look for a primitive of this fellow. Primitive of this fellow will be essentially e power I t and this. So are you following? Therefore our guess is psi of t equal to f of a plus r e power I t into e power I t. Then d by dt of xi of t will be, as we did earlier, f dash of a plus r e power I t into the derivative of this with respect to t, right? Therefore r will remain, I will remain, e power I t will remain, and then there is another e power I t plus f of a plus r e power I t into derivative e power I t will be e power I t. Do you understand this? This is the derivative of this fellow with respect to t. Okay, but this is precisely our whatever we found out. This is del phi by del r or whatever it is. Okay, that's the integrand in the definition of g dash r. Okay, therefore g dash r is going to be 0 to 2 pi of del xi by del t dt. Notice that these are all, again, as I explained earlier, these are all continuous functions of, now r, continuous functions of two variables r and t. Right, this is again a continuous function of r and t. Right, therefore I can apply fundamental theorem of calculus. So what do I get? Therefore it's going to be xi at 2 pi minus I at 0. But what is xi? Let's look at xi. Now you can see xi at 2 pi is same as I at 0, because where it matters in t. In the t variable, what happens is e power it, but e power it is periodic with period 2 pi. Right? Therefore I get this. Therefore this is equal to 0. So that proves g prime r is 0. Okay, for all r in r1, r2, or whatever it is. Therefore g is a constant on r1, r2. That means integral of f over gamma r will be integral of f over gamma s for any r and s in r1, r2. Okay, so we proved it. Go through the proof. This is a very easy proof, except it okay, only subtlety is that I have to use the fact that f is infinitely differentiable, and hence f dash exists and it's continuous. Yeah, it's simply holomorphic, simply means f dash exists. I do not know whether it's continuous or not, but we needed that fact. Okay, please review the proof once more so that you will be very comfortable with that. Next thing, we will make use of this to derive what is known as Cauchy integral formula for the annulus. Okay, this is what is needed. Okay, we will go to that next part.